So, I got this assignment from Dr. Talmadge last week, and I wrote back, and Andy wrote back to me, and I had a change of heart. I've always thought that there were certain threads that should weave through the curriculum from elementary school to high school. Um, I base this on what I see as outcomes that we'd like to see for students, and I've sometimes been disappointed in the outcomes, and I think that's possibly because we haven't done a good job um, building to those outcomes through elementary, middle, and early high school. Well, the most obvious missing link in computer education um, is we don't pay much attention to iteration and feedback at any level. Whereas I think this is perhaps one of the most important topics we could deal with in mathematics and science. One of my pet peeves is calculator literacy. Uh, I find that most students and most math teachers don't know how to use their calculators. They can add, subtract, multiply, divide, and graph something, and that's about it. Um, unless they take, say, a statistics course or some other advanced course in which the teacher is into using this sort of stuff. They really don't learn how to use it, and that's a mistake. Uh, the same thing really applies. It's not just calculator literacy, it's mathematical computer literacy, knowing how to find the proper software to check their work, to confirm their work, to drive home concepts. Systems analysis. NASA started systems analysis, probably invented the term, I guess, back in the late 50s when they were trying to begin the space program. It was going to be the greatest thing since sliced bread, and it's been getting pretty moldy in the pre-college curriculum over the past 40 years, 50 years or so. The related topic, which is very appropriate to mathematics education, is systems dynamics, in which you look at things like iteration and feedback and the interaction among a variety of different factors in some sort of a system, and make projections and estimates and predictions about what might happen. This is something that the software has been available for, maybe 30 years, I guess, and it's pretty good stuff. And it's easy to use, and almost nobody uses it. And this is another one of my pet peeves, even though I myself didn't take advantage of this. So if we're going to revolutionize the mathematics curriculum when it comes to computer programming and related topics, that means we have to weave these threads through the curriculum, which means we need weaving lessons. We need ways to teach kids this. Here are a few thoughts on weaving lessons. One of the best ways to teach iteration and feedback is through spreadsheets. And the advantage of this is that spreadsheets, unlike a lot of the stuff we use in high school, that's software, that's materials that are going to be available to the students in college and beyond. So if they can learn to use something like Excel and use it well and understand what's going on when they use it, that can make a big difference in how they perform later on in life when they try to accomplish certain tasks. Stella and related software. It's the systems dynamics software known as Stella is very, very expensive and I don't necessarily recommend buying it, but there's other available stuff, particularly in the NetLogo free software. They've got some real nice systems dynamics options, and there are other free versions and also cheaper versions. And let me show you what this is. This is a NetLogo systems dynamic model of an epidemic. And we've got 3 boxes here, and these are called stocks. And each box contains a certain number of people. Originally, you're going to have a few sick people who have the disease. Just about everybody else is going to be uninfected over here. And the sick people, see this little valve here? The bigger that valve is, the wider open it is, the more people are going to get infected. And we have a simple formula for figuring that out, which is not perfect, but it's not bad. And that formula basically is we take this constant K and we multiply it by the number of sick people and the number of uninfected people. And you can see K times uninfected times sick gives us the rate of change of infection, because sick people, the more sick people you have, the greater the infection. But also the more uninfected people you have, the greater the infection, because there are more people for the sick people to bump into. And eventually both of these populations, we hope, would go down. So, and then the sick people, they eventually get well. And we kept it simple. We just have a certain fraction of them getting well over every time period. This is broken up into discrete time periods. And notice this is a real simple model. All you have to do is drag these connectors, come up with the basic formulas. There's no calculus or anything like that involved, even though calculus is at the heart of this. All of that is done behind the scenes. And here's our setup, and we start out with a certain number of sick people. And in this case, I have 26 sick people. We have 160 people in the little town. They're uninfected. None of them are recovered because none of them have actually had the disease for any period of time. We've got this infection slider, which we've got set at 0.01. And we have the uninfected sick slider, which we can change, but we've got this, they set at 20 and 160, and then we go, and it gives us the model over time. This is a fairly sophisticated model for young kids to be working with, but the amount of math required is not very much at all. And basically what you have to know is what factors affect what other factors, and how do I relate them to each other in my diagram. So that's systems dynamics. Just to point something out, you'll notice it's systems analysis, although you can call it system analysis. And it's system, I said systems dynamics. It's more often just said system dynamics and system dynamics models. Okay, so now here's the tough topic, programming. And I'm about as clueless as anybody as to what's really going to work, and that I do have my prejudices like everybody else. Okay, the first rule of programming, at least for beginning, is KISS, keep it simple, stupid. And about the only way that this is going to work, certainly at an elementary school level, is select some sort of language where teachers and students can learn and have fun together. One of the big problems with mathematics, I think, and I could be wrong, is we don't do a very good job of training teachers who are non-math teachers how to teach math. And because of that, that's one of the reasons why we have problems later on with students not liking math, not doing well in math, being frustrated by mathematics. But if you have a programming language in which teachers and students kind of struggle together, but the struggle isn't all that great, then there's potential, at least for something like programming to be done in a successful manner. Well, why programming? Several reasons. One is, primary is, it's really great for systems analysis. It's really great for teaching and applying iteration and feedback. It's fun. It produces results that um, give students incentive to want to learn more. Uh, Andy has had some success with Andy and Jerome actually have had some success teaching some really bright, excited kids the language Scratch in a summer program. Uh, I put Scratch and Sniff, but there is no Sniff language. It just sounded funny. Um, and at St. Martin's now, and I think it's in fifth grade, one of the tech people is teaching students Scratch. And she started out with really no knowledge of it, just some good computer skills. And she's been learning along with the kids. It's very well documented. You just follow through the lessons. And she's really excited about this and is seeing some good results from kids, and the kids are excited too. So I think there's a lot of potential here for languages like Scratch, and Andy can tell you more about it at some other time, or maybe even today. I've always been a fan of the language called BASIC, just because it was easy to teach myself. I had a little semester of Fortran back in 1963 or 64, and that's kind of been the basis for teaching myself languages from then on. And BASIC is very basic, and it's easy to use. And the Visual Basic language is one that I've taught in high school, and VBA, Visual Basic for Applications, is something I'd really recommend instead of Visual Basic, because it's built in to Excel, so you can actually do some programming with Visual Basic for Applications. And let me just show you what can be done with that. Okay, remember that epidemic model that we had? And that we did using NetLogo? Well, here's essentially the same model done with Excel using Visual Basic programming in the background. So we aren't really using the spreadsheet commands very much. We're using some programming commands along the way. So here we go. Let's initialize things. And here we go. We got 5 people who are infected times 0. We go one step at a time. And they bump into people and they infect them. And we get, over time, our model. And we can see that the curve kind of looks like a logistic curve until eventually everyone is infected. And once you get this data, you got the graph of it, you could do a curve fit, and then you could do it again to see you get different data, but the same basic shape is pretty much the same. Let's go ahead and do that just for funsies. Let's start out with, let's do 27 infected people. We initialize it. And we move along, and we see, because so many people were infected at first, that the infection goes up much more quickly. But again, we have essentially a logistic shape, and all this is done randomly. And here's most of the code that actually makes things happen. If you've had any programming in BASIC, you can see the old for next loops, and the only thing that makes this different from regular Visual Basic program, or the essential thing is that we have a way of connecting the programming here to the individual cells. You see we have cell names and numbers here, like row 2, column 22, and that enables us to use our programming to control the spreadsheet. Extremely powerful, extremely useful to someone who goes on and uses a spreadsheet to do things like presentation in the work world. I'm not going to say too much about it, but of course Geogebra is a wonderful tool we've talked about here before, and I'm sure we'll be talking about it some more. And it teaches kids to do logical step-by-step thinking, and that's what we're talking about here. That's what this is all about. So I strongly recommend using Geogebra, and I think it's simple enough to use on elementary school levels, but I could be wrong. I haven't been in elementary school in a long time. Programming with the graphing calculator provides kids with a wonderful opportunity to do some logical thinking. And there's a real incentive for them to do some programming because it enables them to um, simplify some of the work they have to do. But if they're going to do it doing their own programs, they have to understand the concepts that are involved. For example, suppose kids are learning about the Fibonacci sequence. They can sit there and very easily generate many, many terms of the sequence. But if you ask them to write a program to generate the sequence, then you're talking about a different level of understanding of what's going on, I think. And it's not that hard to do. There's a Fibonacci program, what, a dozen steps or so. And in doing it, the kids can get a lot of satisfaction in seeing that they can actually, of course, generate many, many, many terms on their own without having to do all the work. And that's pretty cool. Students, just like us, like labor-saving devices. And if the labor-saving devices can be generated with a little work involved in it, they're not all that disinclined to do it if they can see the results and if it makes life easier. So I'm a big fan of calculator programming, even though the programming language is pretty much of a pain in the butt to work with. So those are some ideas. My basic philosophy has always been don't be afraid to jump into the water even though everybody else is holding back. Um, you can almost always get out if it's too cold. And sometimes you find that it leads you to new depths that can be very, very satisfying in the educational process.